All right, welcome to the seminar series, or the part of the seminar series where we actually start to code. So the last couple videos I've been posting, I've been doing an overview, and then I went into translational dynamics, and then I went into the orbital elements, and then rotational dynamics. I went into sensor dynamics, and then finally B dot control. And so now it's time to code all of this. This first slide there's not really much going on in here. This is more of like an overview of how everything works. So really, when we start to code, we really need to talk about this one. Now, this slide here, though, it's really important for us when we start programming the derivatives routine. I want to have everything in here sort of look like this, and that I want to have like big functions that are called like guidance and control and satellite navigation. So that's sort of like the systems engineering part of this video, where it's how do I want the code to work, and I'd like the code to have all of these different modules. And so today I think I'm just going to create the satellite module, and I'll do the other modules later. And not only am I only going to do the satellite module, but I'm only going to do the translational dynamics in this video. I'm going to need the orbital elements in here eventually, but for now I'm just going to do the translational dynamics. And so to code this translational dynamics, I need to be able to code F equals ma, and basically I have a differential equation, so I need to use ode45 to integrate these equations in motion. And so if you, the main kernel of ode45 is, and ode45 stands for ordinary differential equation 4-5, which is a Runge-Kutta 4, Runge-Kutta 5 adaptive time step. And it's been a while since I've coded in MATLAB, so I'm actually going to type in help ode45 to see how this works. So the outputs are the time vector and the state vector as an output. ode45 is a function. You need to give it the derivatives function, so I'm going to call it satellite. You need to tell it how long you want to simulate for, so I'm just going to give it t-span. You need to give it the initial conditions, and then I'm gonna say no options. Okay, so let's comment this. This is where we integrate the equations of motion. And so we need a couple things. So the first thing is need time window. Okay, so I'm going to first put this around Earth, just because I think I know that pretty well. And so before we do the time window, I actually want to do the initial conditions. Now I'm doing translational dynamics, so I need an x0, a y0, and a z0. Now, in order to get these initial conditions, though, I want to be able to program, oh yeah, and by the way, I also need x dot 0, and I need y dot 0, and I need z dot 0. So I need the initial position and the initial velocity, and then state initial is going to be x0, y0, z0, x dot 0, y dot 0, z dot 0, and that's it. Okay? So we need, in order to put our system in orbit, we need to put this at some altitude above Earth. So I'm going to say altitude. I'm going to put it, let's look up where the International Space Station altitude. Okay, so let's see. It's at 254 miles above AGL. So 254 times 1.6 times 1,000. That gives us meters. Okay, so that's how many meters above the Earth we are. Then we need to look up, and I'm going to make a function called get planet parameters, and I'm going to call Earth, and hopefully Earth does not exist. No, undefined function of variable Earth. Good. So I'm going to, and actually I'm just going to call this planet. Okay, just in case we want to put a different planet in there. Okay, so planet doesn't exist, so I'm going to edit planet.m, and I'm going to create it, and this will define all of our planet parameters. Okay, so a couple things. So first I want the radius of the planet, all right? So let's go to radius of Earth, all right? And we've got, where's my meters here? Come on, there we go, whoa. Okay, let's see, so 6.3 million meters, so that's what, E6? Let's see, 1,000 is E3, and then 10, a million, yeah, a million is E6. So it's meters there, okay? I want the mass of the Earth in kilograms. Mass of Earth, oh great, 5.972, 5.972 E24. So that's mass. From heat, I also want the gravitational constant. Gravitational constant in SI. Let's see, 6.67 E11, 6.67 E11. And this is in kilograms, and this is in some SI unit. It doesn't really matter. I'm also going to compute mu, which is G times M. And then I'm going to skip ahead a little bit, but when I get, if you remember my orbit, the velocity of a circular orbit is square root of mu over r. No, I actually don't want to do that yet, so I'm just going to leave that. Okay, so I've got mu, so I think that's everything I need. So then up here, back in main, I'm going to run the planet, and then so my initial altitude, or my initial x-coordinate is going to be r plus altitude, okay? Then I'm going to make y 0 to make this easy, and then z 0 I'm going to make a 0 as well. So basically, if I have the Earth, I'm going to be along the x-axis and no y and z component, right? If I have my x, y, and z axes and I have the Earth in the center, I'm going to be out x, no y, and no z. So I'll just be out here right at the equator. Now what I'm going to do with the velocity is that I'm going to vary, x would be the velocity normal to the surface of the Earth, and I'm going to make the system, I'm going to make the satellite just have a completely tangential velocity, so it's going to be tangential to the surface of the Earth. So x dot is going to be 0, but y dot is going to be v circular, and I'm going to times it by sine of the inclination, and then I'm going to do v circular times cosine of the inclination. And then that way I can give the orbit an inclination. Right now, I'm just going to make the inclination 0, and so we're just going to be looking at a completely equatorial orbit. And I need to make sure that I think this is actually supposed to be cosine, and this is supposed to be sine. I think I have that right, because when cosine of 0 is 0, so that's x, y, yeah, so that'll be completely around the Earth there. Okay, so I think I have my initial conditions, so that's good. So then I can make my time window, right? And so the reason why I wanted to get my initial conditions first was because what I want to do is I want to, and it doesn't look like I have it here, so what I'm going to need to do is grab, let's see, the fundamentals of astrodynamics, and there is an equation in here. This is a PDF that was written in the 70s. There's an equation in here that tells you the period of an orbit as a function of semi-major axis. And I want to say it's 2 pi over square root of mu. It's in here somewhere. I don't want to sit here and look for it forever. I'm just going to guess. I'm going to say that the period is 2 times pi over the square root of mu times the semi-major axis raised to the 3/2 power. Okay, and then the semi-major axis, and this, again, this is why I wanted to do this, is equal to x naught. Or I'm going to do the norm of x0, y0, z0, just in case you want to take this code and do what you want. Oh, and then by the way, in my MATLAB, I'm doing this in MATLAB because I could have done it in Python, but I felt like doing it in MATLAB. I guess I don't really have an answer to that. But I have a GitHub for MATLAB, and I made a new folder called ADCS Seminar Series. And so every time I make an edit to this code, I'm actually just going to make a copy of it. And so this one will just have the main and the satellite module in it, and I'll make a subfolder for that, and then I will edit it from there and add a new one every time and push it to the cloud, so you'll have this. Okay, so we have the period. So so now I can do t-span is 0 to the period times number of orbits. So I can actually tell it how many orbits I want. And for the first time I do this simulation, I just want one orbit, okay? All right, so I have the t-span, the initial conditions. Now I need to make the satellite module, okay? So let's come down here, edit satellite.m. And this is a derivatives routine, and this is going to be a function, so it's going to be dstate dt is equal to satellite, and shoot, I always forget. Let me do help ode45 again, and let's see, does it tell you? Okay, it's a function of t and y, so t is first. So you need to tell it that it is a function of t and then the state vector, okay? Now, the state vector is going to look exactly like this vector here. So I'm gonna just copy this and put this here for now. And remember, this might change, right? If we start adding rotational dynamics in, then this is gonna change. But for now, x is gonna be state of 1, y is state of 2, z is state of 3, and I don't think I really need to pull these out per se. So let's figure out what we need to do here. So at the end of the day, I need to return dstate dt, which is going to be the velocity and the acceleration, okay? So let's think about the velocity. That one's pretty easy. The velocity is just x dot y dot z dot. So that means that the velocity is the state of 4 to 6. So that's the 4th, 5th, and 6th element. Let me go ahead and finish this out, these comments. So that's x dot, state of 4, y dot, state of 5, and then z dot is state of 6. Okay, how am I doing on time here? 12 minutes? Yeah, okay, let's get moving. We're almost done here. Okay, so we got the velocity, so now we need the acceleration. The acceleration is f divided by m, okay, which means I need a mass of my spacecraft. So I'm gonna assume that I've got like a simple CubeSat, so it's 2.6 kilograms, okay? This is typically called the kinematics, and then this is typically called the dynamics, and I'm gonna put inertia parameters here, inertia and mass, because eventually we're gonna need to put the inertia of the satellite, okay? And again, if I'm going too fast, I'm trying to make these videos short. My recommendation is to watch this, pause it if you need to, and then watch it again if you need to. Go download the code on GitHub. This is not a follow along exercise. This is sort of a show and tell, okay? All right, so now we need force. So for that, I'm gonna go back to the board notes. So let's see, board notes, and here we go. So I'm gonna ignore radiation pressure, aerodynamics. I'm gonna ignore thrust as well. And so I just need F of gravity. So I'm just gonna say F grav, and then I guess here I'm gonna put force, I'm gonna put a gravity model in here, gravity model. And so I need to program this gravity model in here. So I need to run the planet again, okay? And remember, the planet is just this script here that sort of gives me these parameters. So that'll give me the planet. And then gravity is negative g times the mass of the Earth times the mass of the satellite divided by the norm of the distance from the origin to the satellite squared times this vector r hat. Okay, so that's a lot altogether. So first, let's compute r hat. So r hat is r divided by the norm of r. Okay, well, what's r? Well, r is x, y, and z. So that means so r is equal to x, y, z, and since the state vector here, the first 3 states are x, y, and z, I just need to grab 1 through 3, and that's going to give me r. And then r hat is just r divided by the norm of r. I'm also going to create an r norm, and I'm going to do norm of r like that, and then I'm going to replace this with r over r norm. And the reason why I'm going to do that is because F grav is negative g times mass of the Earth, so that's capital M. So the mass of the Earth times the mass of the satellite, which is lowercase m, divided by r norm squared, and then that whole thing is going to be multiplied by r hat. Okay? And then that's it. F grav is this, g times m of the Earth, m of the satellite, r norm squared, r hat. Acceleration is f divided by m, and then return derivatives vector. Okay? That should be it. So let's see if this code runs. Let's hit an F5 here. And it says undefined function or variable altitude, because 9 times out of 10, it's a typo. Okay? Undefined function or variable, v circular, right? So v circular, remember, is from the equations, it's square root of mu over r. So square root of mu over r. Remember, r is defined in here, but it is not defined over here. So I need to do the square root of, no. I can do the norm of x0, y0, z0. And I feel like, didn't I make that variable down here? Yeah, that's the semi-major axis. So I'm actually going to put that here and then get rid of that here and then just divide this by the semi-major. So I'm doing circular orbits here. This code will work for any orbit. My initial conditions will only work for circular orbits. Okay, so the simulation worked. Let's go ahead and plot some stuff. Plot. Let's plot just the 3D orbit and then be done with it. Okay, let's just do something simple. So plot 3D orbit. So I need to make a figure window. Let's do fig equals figure. What do we want to do? We want to do set fig color white to make a white background. We want to do, how do you change the font size? I think I forgot how to do that, but that's fine. So let's do plot 3. Let's extract the state vector. So x out is state out of all comma 1. So let's actually look here. So state out is 101 rows and 6 columns. So the first column is x. The second column is y. And the third column is z. And so I should just be able to do x out, y out, z out. I'm going to do a blue line, make a line width of 4. Let's throw a grid. What is it? Grid on. Let's throw a hold on just in case we want to plot multiple things. Do we want to put a sphere at the center? Yeah, let's do that. Is it sphere? Oh gosh. Yeah, it is. Okay, cool. Let's do that. But I think it's what? It's x. It's x, y, z equals sphere. Here, let me just type in help sphere. So sphere, generate a sphere. N gives you the 3 n by 1. So you can tell the number of data points you want. If you just do sphere, it's 2. Okay, and then we can scale it up. So yeah, so let's make an Earth. And so let's do x, y, z is sphere, and let's just do the default. And then we need to scale it up, so we'll say x is x times r, the radius, and then y is y times r, because this is going to make a unit sphere. And then down here, since we did the hold on, we can just do, let's do surf, not mesh, I like surf, x, y, z, and then let's do like edge, color, none. I think that's how it works. Let's try that, see what happens. Oh boy. I got my equatorial orbit for sure. Oh no, it plotted. Is it clipped? What's going on here? Yeah, it's like it wants to show a sphere. Can we do axis square? Axis square. What if we, this is so wild. I've never encountered this before. Where it clips in and out. That's wild. It's like the rendering environment. You know what? What if we did, let's do 100 points. Maybe it's just a, oh man, it's still, all right, well, I'm gonna leave it out. There's our Earth. it's a weird clipped cylinder, but what if we plot in kilometers? I like that idea better. Let's do divide everything by 1,000. What's my time here? Yeah, I'm at 20 minutes. I don't want to spend too much time on here. So I'm going to take, let's see, convert state to kilometers. So state out is equal to state out over 1,000. Okay, so now, yeah, so I think I must have just run out of bounds. So now there's the Earth at a certain kilometer. There's my inclination, my orbit. I am at the, what is it called? I'm at the altitude of the ISS. That is so freaking close. Let's actually do the inclination of the ISS. So what is the inclination of ISS? I feel like it's like, 51.6 degrees. Oh, that's pretty sick. You can kind of see, yeah, that's a pretty cool, you can kind of see like where, so let's see if we can actually get an image like this. So let's put the inclination at 51.6. We got to multiply by pi over 180, right? Because it's got to be in radians. And then boom. So there's our 51.6. I may have gotten the signs wrong. Like maybe this one needs to be negative. Yeah, that seems about right. Let's put mine next to theirs. How do I do this? Boom. Look at that. 51.6 degree inclination. We got it. Okay. Should we try like a higher orbit? So maybe instead of 254 miles, let's do 10 times that amount. See what happens. Look at that. Now we're super far away. I think the axis square is not working. I think we need to do axis equal. Now we're talking. That looks like Saturn. That's sweet. Okay, so there's our super far away orbit, 2,000 miles above the Earth now. So there you go. Simple translational dynamics. I'm right at 22 minutes. I'm going to call it there. If you have questions, post in the comments. Again, it is in Github or matlab.git and then ADCS seminar series. I'll post a link in the description. And if you have any questions, post in the comments, and I hope you stick around for the next video.